All right, we've got one more video here for activity 13. And we're still talking about asymptotes, these rational functions. And we have seen, and specifically in this video, we're talking about end behavior. What happens as x goes to infinity with these functions? We have seen two different possibilities in the two previous videos. In the first video, this last example, on this question here about horizontal asymptote end behavior. As x goes to infinity, we saw that the numerator and denominator, they were both linear expressions. The highest powered term, they had the same power. And so what happens as x goes to infinity is that those terms basically undo each other. Not undo each other, but kind of cancel out, leaving us with the coefficients on those terms, 5 over 2, which we determined in that one to be 2.5. We saw that same situation in example 3 on the previous video. The highest power term in the numerator and the denominator, they were both quadratics, x squared over x squared. So as x goes to infinity, those terms are going to cancel out, and we were left with a horizontal asymptote of y equals 1. So that's what happens when the numerator and denominator, when the highest power terms are the same. We also saw in example 2 what happens when the highest power term in the denominator is larger. As x goes to infinity, if my denominator is getting much larger than my numerator, then with fractions, as the denominator gets bigger, the fraction itself gets smaller. And what happens is that our end behavior is going to approach 0. So if the highest power term in the denominator is larger than the highest power term in the numerator, then our end behavior is going to approach 0. But what happens when the highest power term in the numerator is the one that's greater? Well, if x is going to infinity and my numerator is getting much bigger than my denominator, well, that means that this whole expression is going to approach infinity as well. It's going to keep growing because my numerator is bigger than my denominator. However, there's still going to be a type of boundary on that growth, and we call it a slant or oblique asymptote. And so I'm going to show you here one way to figure out what that asymptote, the equation of that asymptote would be, and I'm also going to show you the graph so you can see what it looks like. The way we're going to do this is we're going to rewrite this expression by using long division. So x squared minus 3x plus 7 divided by x plus 1. So I'm going to divide this out. What do I multiply times x to get x squared? That, of course, would be x. X times x is x squared, and x times 1 is 1x. And now we're going to subtract. I'm going to make sure I change the sign on both of those terms. My x squared 0 out, and negative 3x minus 1x would be negative 4x. And then I'm going to bring down the 7. Now, what do I multiply times x to get negative 4x? That, of course, would be negative 4. Negative 4 times x is negative 4x, and negative 4 times 1, negative 4. We're going to subtract, so I'm going to change both of these signs. Negative 4x plus 4x, those 0 out, and 7 plus 4 is 11. And I have nothing left to bring down, so we're done. Plus 11 over x plus 1. So now that we have divided that out, what this means is that this is a way I can rewrite this function, x minus 4 plus 11 over x plus 1. So first of all, let's talk about the vertical asymptote, because we already know how to find that. Your vertical asymptote happens whenever the denominator is equal to 0, as long as it's a factor that you don't have a matching factor in the numerator, which we don't here because our numerator doesn't even factor. So I'm going to set my denominator equal to 0, which means x equals negative 1 is going to be the vertical asymptote. And that's what we were asked to find here. The slant asymptote, or the oblique asymptote, is going to be this part of the expression right here. Y equals x minus 4. And let me show you what that looks like on a graph. I've already graphed this rational function for us. So you can see that the ends are going to continue to grow without bound. They're not approaching a horizontal asymptote like we saw in the examples in video 2. This red line here is the line y equals x minus 4. And hopefully you can see it's serving as a boundary for where the ends of this function are going to go. They're still going to infinity and negative infinity, but the behavior is bounded by this linear function. And then, of course, here you can see the vertical asymptote at -1. So that's what a slant asymptote looks like, and kind of how it controls or contains the behavior of the rational function. Let's do one more. X cubed plus 3x squared minus x minus 1. I'm going to divide by x squared minus 1, but notice there's a missing x term. I'm going to go ahead and write that in there just to make sure that I account for that term in this quadratic. So what do I multiply times x squared to get x cubed? That, of course, would be x. X times x squared is x cubed plus 0x minus x. And we're going to subtract. So I'm going to change all the signs. X cubed minus x cubed, those zero out. 3x squared minus 0x squared. Whoops, I forgot my squared on the x there. It doesn't matter because it's 0, but I should have it. That would be 3x squared. And then negative x plus x, those zero out. And then I'm going to bring down minus 1. What do I multiply times x squared to get 3x squared? That, of course, is 3. And I'm going to subtract, change all the signs. My 3x squared, 0 out. The 0x's, 0 out. And -1 plus 3 is 2. Plus 2 over x squared minus 1. So now we can rewrite this function as x plus 3 plus 2 over x squared minus 1. And so if we follow, excuse me, the same pattern as we saw in example 1, our vertical asymptote is going to come from setting our denominator equal to 0. And you could factor that. You could just add 1 and square root both sides, however you want to think about it. But either way, we get x equals -1 and x equals +1 is the vertical asymptote. So I'm going to make that plural. We've got 2. And our slant asymptote comes from this part of the expression right here, y equals x plus 3. All right, on example 3, last example, write an equation for a rational function whose graph has a slant asymptote with this equation and a vertical asymptote at x equals 5. So here we're just thinking about these same ideas, but in reverse order. So I'm going to call this function g of x. And if it has a slant asymptote that's y equals x minus 4, well, then I know I'm going to have x minus 4 here. Plus, if I have a vertical asymptote at x equals 5, that means that my denominator needs to be 0 whenever x is 5. So my denominator has to be x minus 5. And then we just need a number in the numerator. And it just says write an equation, not the equation. So there's a lot of right answers that we could have here. We're just going to put a number up here. I'll put 6. And so that would be an equation that would have a slant asymptote of x minus 4 and would have a vertical asymptote at x equals 5.